In this video, we'll walk through every 3D joint Unity offers, how they work, when to use them, and when not to. We'll look at some prerequisite information that you need to know before using joints, discuss all types of 3D joints, learn some important concepts to add dynamic behavior, and learn how to code and tweak these joints. Let's dive in. So, what are joints to begin with? Joints are used to connect two rigid body objects together or connect a rigid body object to a fixed anchor. They restrict or allow movement in specific ways. They let you attach one object to another, let them rotate, slide, or spring, all while adding realistic physics movement. You'd use joints when you want to swing open a door, a character to fall apart like a ragdoll, a swinging rope or chain, a platform that jiggles or bounces under weight, or create a machine with parts that move together. Do you need to be a physics expert? Not at all. But you should have a basic idea of what rigid body component does. Know what mass, drag, and forces are. Have some idea of Unity's physics system, like fixed update, colliders, and gravity. But the most important aspect of it is experimentation, aka trial and error. Joints will feel complex at first, for everybody. But they will only become clear to you through experimentation and not watching a tutorial. Play around and tweak the settings and see what they do. That's how you actually learn. Let's look at some prerequisites you need to know before using joints. It's important. Firstly, both objects to be connected must contain a rigid body component. If you don't know what a rigid body is, adding it to a game object simply tells Unity, hey, this object should follow the laws of physics. And when you start connecting objects using joints, how you set up your rigid body matters a lot. Let's start with mass. Mass affects how heavy the object feels to the physics engine. A heavier object will restrict movement, while a lighter one might get pulled around like a balloon. Here's the thing, mass can cause imbalance and will cause weird behavior. And only one way around it, experimentation. Always think about mass logically. Should one of these be heavier? Or should they match? Let's say you are jumping on a platform and the player has mass 5 kilograms. Then the platform in itself should be heavier than the player so that it can support the weight of the player. Otherwise, it will go down because the object on top is heavier. Next is use gravity. If it's on, gravity pulls the object down. But when you are working with joints, you might want the gravity on one object and off on another. But turning off gravity doesn't mean that it won't react to other forces. It can still react to everything except gravity. In order to not react to other forces, you need to set the rigid body object to kinematic. This checkbox simply says, don't let physics control this object. I'll move it with code. This is great for two things. When you want a static anchor object that doesn't move at all, or when you want to animate the movement yourself, while the connected rigid body reacts. Just beware that a joint won't work if both connected objects are kinematic. There needs to be at least one rigid body the physics engine can push around. Setting the body kinematic also doesn't let the gravity affect it. The last and probably one of the most confusing things to understand are constraints. Constraints in rigid body locks certain motions. For example, you may freeze rotation on all axes to prevent an object from spinning. If you want a platform to move only up and down, you can freeze position X and Z. Why is this important? Because joints themselves are like dynamic constraints, meaning they would still do it, but they can be changed later via code. Or there are more rules to when and how these joints work. If you already lock an axis with a constraint and also try to limit it with a joint, they can clash and may cause strange results. So I want you to think of it this way. Rigid body constraints are at the top level, higher priority. They are hard rules. You limit something, it takes things seriously. Joints are flexible constraints, meaning you can reference them via code and change the settings to add more spice to gameplay. They also contain other rules like break force, which will add more life to the constraints applied on the object. Joints don't just stick things together, they also add physical behavior. like making things springy and loose between two rigid bodies. I'm telling it to you now. You will never get it right the first time. It's all about experimentation. Before we get to each type of joint, it's important to understand some basic properties common to all joint components. I'm using fixed joints as an example here, but you will see these properties in all other joints. The most important one is the connected body. This is the rigid body that your joint will connect to. If you leave this empty, Unity assumes the joint is connected to the world. This means the object is anchored in place. This is best when you want the joint to be anchored to an invisible spot in space, without needing to create or manage an extra rigid body just for that. We'll look at it when we make physics doors in just a few minutes. Brake force and brake torque is the maximum force and the maximum rotational force, or torque, required to break apart a joint respectively. This is powerful. This means you can break or destroy this joint component on adding an external force. This allows you to create destructible objects in the cost of physics. Setting it to infinity means it won't break no matter how much force is applied. Enable collision allows the two connected objects to collide with each other. By default, they won't. It's often left disabled to avoid unwanted jitter or pushing. Leave enable pre-processing on to make the physics behavior more stable. If you turn it off, you'll get more realistic but unstable behavior. I recommend turning it on. Mass scale adjusts how much the current object's rigid body's mass affects the behavior. And connected mass scale is similar, but for the connected body instead. They help you fine-tune how mass difference between objects influence their movement and stability. I believe they are used for balancing heavy and light objects in a joint setup. Setting it to 1 means there will be no biasing. It will use the mass in the rigid body for the calculations. Change this to something else to add bias to the laws of physics. Now let's break down each individual 3D joint and learn what they do. There are 5 different types of 3D joints, and let's learn them in the order of complexity. Fixed joint, hinge joint, spring joint, character joint, and finally the configurable joint. There's also a special component called the articulation body, which is used for robotics, advanced simulations, and precision rigs. We won't be covering that in this video, but let me know if you're interested. I have never used this as well, but I would be happy to research them for you. Joints for 2D are also different. Let me know if you'd like a video on that. Let's start with the fixed joint. Fixed joint locks two rigid body objects together. That's it. Let's look at this example. There are 3 rigid body cubes stacked on top of another. We can add a fixed joint on the top one, drag and connect the middle one as its connected body, meaning whenever the middle one moves, it also moves along with them. And the middle can also have a fixed joint, and we can drag the bottom one as the connected body. Now the two objects form a chain of joints and will move if the base object undergoes physical operations. Fixed joints are used to glue things together. This means even if you move the joint rather than the connected body, it will still remain intact. So the order of connection does not matter in fixed joints. Now this is not a good practical example of using fixed joints, but I added it just to get the idea across. It's basically like we are parenting the objects in a hierarchy, but we are not. We can break this parenting dynamically by adding a brake force. We can shoot a projectile or something to break this joint and make it normal rigid bodies. Like I said, it is not a good practical example, so here is one. Let's make a hanging bridge. I will create a simple plank, add a rigid body to it, then duplicate it to make a bridge. Then I will select both planks at either end and then freeze position so that it doesn't move. I am not setting it to kinematic as I want it to rotate when the player lands on the plank. Then for all in-between planks, I add a fixed joint. I will connect plank 1 to left end plank, plank 2 to plank 1, plank 3 to plank 2, plank 4 to plank 3, and finally add a fixed joint on the right end plank and connect it to plank 4. We have created a chain of fixed joints here. We can also add a brake force if we want this bridge to break. Now if we play, we can see the hanging bridge. But walking on it causes it to be like we're in Squid Game. The planks only need to rotate along x-axis. So we need to freeze rotation y and z on all planks. Now we have a hanging bridge. We can play around with the mass scale, but better change the mass of the planks or the player. In this case, let's add weight to the player. Now the bridge feels more dangerous and alive to walk on. We'll talk about optimization later as well. Next up is the hinge joint. Hinge joint allows the body to be rotated around one axis depending on an anchor position. For example, doors, wheels, seesaws, I don't know. This is one of the joints that allows you to add custom anchors, meaning you don't really need to have a connected rigid body, which is nice. But you still can have that. Hinges are primarily used for rotation, like doors, levers, or even a chandelier hanging on the ceiling. Let's make a door that can be moved by physics. I have a simple door with door frames. All of them have box colliders. To make the door move by push or pull, let's first add a rigid body to the door. I recommend not changing the constraints for hinges, and the rotation constraints can be controlled dynamically through the hinge joint. Like I said earlier in this video, we don't want these to clash. For doors, you don't need any connected rigid body, but you can change the anchor position. If you zoom in on the scene, you can see this very tiny yellow arrow for the anchor. Now you can set the anchor to the place you want to rotate around. In my case, after trial and error, it is negative 0.5, negative 0.50. We also need to specify an axis to rotate on. I want to rotate it along the y-axis. So I will give 0, 1, 0. This is just a normalized vector. You can also use spring effects on the door. Also you can use motor, which makes it as if the doors are possessed by ghosts, and you can make them open and close based on velocity, force, and spin. The most important one is use limits. This allows you to add constraints to the angle of rotation. We don't want the door to do a full 360. It should stop somewhere. Once you do that and press this Edit Angular Limits button, you will see two handles in the scene view, and you can drag it to add a min and max angle for the rotation. You can hold Ctrl to snap it to increments of 10, I believe. Or you can open this limits fold out and then set it manually over there. Now if I play the game and move through the door moves the way it's supposed to. If I don't want it to open that quickly, again, trial and error is important here, I can increase the mass, and then it would need more force to open. Because hinge joints are really useful, I'll give another example, just to show you how powerful they are. I'll show you how I made this slider crank mechanism, all using hinge joints. You see, hinges are used for rotation around an anchor, and the position adjusts accordingly if needed. This crank needs to continuously rotate, so I added a hinge joint to it, made the mass high through trial and error for the mechanical feel, and then used a motor to continuously spin it. Then on the arm, again a hinge joint, which is connected to the crank and anchored over here, so it rotates, keeping the position over there itself. You see that? In order to connect the base to the arm, I added another hinge joint to the arm and connected the base. Also set the anchor. The only thing I have changed in these two hinge joints are the connected bodies and the anchor position. I anchored the second one there so that the arm doesn't fly off. It stays there and pulls whatever it is connected to. And finally, on the base, just a simple rigid body is enough. I prefer higher mass than the arm, and then I restrict movement along y-axis and froze all rotation. Remember, these are hard constraints figured out through trial and error, and they're used to avoid unwanted jitter. The crazy thing is, the only thing that is originally moving is this crank here, and that is through the motor. and everything else gets pushed along nicely. Again, I spent some time on this and only then I got it working as I wanted to. Hope this helps you understand hinge joints a lot better. Next up is the spring joint. Now, I don't recommend using it on anything mechanical. It is better to use something called the configurable joint or hard code mechanics instead. Spring joint can be used for aesthetic purposes, not to create gameplay centric things like trampolines. But it's very useful in other simpler mechanics like physics based props, dynamic decor, and feel elements. Spring joint is primarily for adding life and natural motion, not mechanical precision. Things like wobbles, swings, and soft reactions to movement. You use it to add personality to props. The whole point of using spring joints, in my experience, is to enhance life in the game. Why is this so? Because rigid body based joints obeys real physics. For a mechanical behavior like a trampoline, we are trying to simulate unrealistic behavior. You cannot break natural rules. So to do these things, we need to fake that behavior instead, using code, sound, and VFX. You're often better off scripting it directly because games break real world physics all the time, and that's okay. In a spring joint, all of these settings are very straightforward. Spring adds more springiness. Damper controls how quickly the object stops bouncing after being pushed or pulled. A low damper means more bounce, slower to settle. A high damper means less bounce, and it stops moving quickly. I tried creating a trampoline using spring joints, and they sort of work well, but they alone cannot be used for gameplay mechanics. Here are the settings for my platform that causes it to bounce. The min and max distances adds a simple distance constraint as well. If I add a force on any rigid body that lands on the trampoline using simple collision checks, then I will be able to replicate a trampoline. Next up is character joints. Character joints are mostly used for ragdolls or bone-like chains. Think of it like a simplified version of how bones in your body move. Specifically, it simulates a ball and socket joint, like your shoulder or your hip. It lets an object rotate around a connected body with limits, but without allowing it to slide away. You will mostly use them for ragdoll character setups. We can use them so that when a character dies, you swap out animation for physics, and these joints keeps the limbs swing realistically without flying off. In this function, we disable the main rigid body and collider, and then enable all the child rigid bodies and colliders for the ragdoll effect. It's pretty straightforward. All of these settings are really straightforward. It's all about trial and error here. Axis defines the twist axis, the main axis around which the body part should bend. Swing defines the axis for forward and backward motion, which is mostly perpendicular to the main axis. Both of these work together to create that fluid, ragdoll, bone-like feel. Twist and swing limits allow you to control how far the joint is allowed to move. If your joints are coming apart, like if the arms are disconnecting, enable projection to pull them back into alignment. A thing to note is that they are meant for limbs and soft constraints. They can get unstable if your rigid bodies are too light or if the limits are too tight. But fortunately, setting up ragdolls is pretty easy. In this example, I have imported a character from Mixamo. You can use any humanoid skin mesh. I have dragged it into the scene. I have made sure that this character is humanoid, and an avatar has been created from this model. Make sure that this base object has an animator component. It's very important. Then we right-click in the hierarchy, 3D, Ragdoll. This opens up the Ragdoll wizard, and you can expand this and set each limb here. But if you have an animator with an avatar, you can simply drag the animator component to this and then apply to let Unity automatically connect the limbs. Now, all of these limbs have character joints attached to them with proper settings and colliders. You might have to adjust some colliders to fit your model. You can also see the masses of the rigid bodies are automatically assigned. If you hit play now, the character falls down to physics. Nice. If you don't want the character to fall down, you gotta set some limbs, rigid body to kinematic. Kinematic doesn't allow anything to affect it. And play around with the joint settings, but then again, it's a lot of playing around. You cannot skip that. And it will be custom to your specific character. You can also control a lot of these values via code, which we'll look briefly towards the end of this video. The final 3D joint is the configurable joint. It's the most powerful joint in Unity. At its core, a configurable joint lets you control all 6 degrees of freedom between two rigid body objects. That's 3 for position, XYZ movement, and 3 for rotation. They're called twist, swing 1, and swing 2. Imagine you have a ball connected to a socket. With a hinge joint, the ball can only rotate around one axis, like a door hinge. But with configurable joint, you can let it rotate freely or limit it or even make it spring toward a certain direction. You can configure the joint and tell what it can and can't do. This is a joint which allows you to do anything. It's like a master joint. There are some new properties specific to this joint that is amazing. This will be a lot of information, so be ready. First, we have a confusing secondary axis field. Primary axis is like the main twist axis. Secondary axis help define the plane for swing motion. What do I mean by this? Imagine a pendulum. The primary axis is going to be the rod's hinge. It twists or moves it left and right. That is simple, right? The secondary axis tells Unity what direction can be used as direction for swinging if needed. So this is the primary twist along the x-axis. And if I show it to you from the side, this is how the swing works, okay? It defines the plane along which it can swing. And it could cause problems because configurable joint allows full customization, which makes it prone to errors. In most cases, it shouldn't be the same as the primary axis. Otherwise, the object might swing weirdly and you wouldn't know what's going wrong. So this is what I'm trying to say. If your joint behaves strangely, like rotating in weird directions or not respecting limits, it's often because your secondary axis isn't aligned properly. In most cases, the secondary axis is perpendicular to your primary axis and points in the direction for your swing to happen. It's difficult to understand this just on theory, but once you play around with the joints, you'll get a solid idea, trust me. It's not that complicated. Next, you get to control linear movement, meaning we can allow or lock movement along each axis. For example, if you lock X and Z, but allow Y, the object can move only vertically. And below that, you get the same control for rotation. You can lock twisting, allow full swinging, or restrict everything entirely. And then you get to customize the limits. It's very straightforward, but it is a lot. You definitely need to use your head here, and you will be prone to trial and error. Now, this is something wacky. You can drive the joint toward a specific position or rotation using target position and target rotation. This means the object will move or rotate to a position and a rotation in local space. You can set it to world space coordinates by enabling this button here. What do I mean by this? There are these foldouts called X drive, Y drive, and Z drive. And you have similar ones for angular drives for the rotation. With this, you can set up how strongly the joint tries to follow the target. Each drive will have 3 key settings. Position spring decides how hard it tries to snap to the target. More string means more stronger it snaps. Position damper means how much it resists overshooting. You want this to be fairly high. Maximum force limits how strong the joint can push. Now, what values you add to this is completely dependent on your game. And you can see this is complicated. So start spring with a moderate value. Adjust it to keep it closer to the target. Leave it to 0 if you don't want any force pulling it. Try 100 to 500 for soft spring behavior and 1000 plus for a stiff behavior. Then add damping if the object shakes or overshoots the target position or rotation. Try 10 to 100. Higher values give smoother but slower reactions. Then set the maximum force high enough to allow motion, but low enough to avoid snapping. So try 1000 to 10,000 in most setups. Use trial and error here again. I know it is complicated, but honestly, it is supposed to be complicated because it allows for full customization, which is why I recommend working with AI tools like ChatGPT for configurable joints to make it a bit more sane for you. Honestly, I have no idea how to work with target position or rotation properly. I just play around, and if it works, it works. You don't and probably will never master this joint. But you don't have to be afraid of using it. It will take up a lot of your time. But once you get used to how this thing works, it's amazing. And finally, projection. It's something that we looked at with character joints. If joint objects get separated too much, enabling projection will try to force it to come back. Projection distance is how far the joint is allowed to stretch before it gets corrected. And similarly, projection angle is how far the object can rotate before it gets corrected. As an example, let's take a look at this platform in which we can jump on and it will bounce. Obviously, you may be able to use a spring joint and use animations to get the same effect. But I thought I should experiment. I only allowed movement on y-axis and limited angular y and z motion for the jiggle effect. Then I just changed the y drive to these trial and error values and just played around. Then I created a simple platform mover script just to dynamically change the target position of the joint so that it moves up and down. This allows me to have more control over things. You can also animate the target position and target velocity instead. That's completely fine. This is just one way of doing it. The whole point is, this is complicated. You will never get this right in the first try. You will probably never get this right in the first time, even with 8 years of experience. Unless you are a physics expert, which most of us are not. But the most important thing is, don't be afraid to see all of this. I'm not expert at any of this. I'm talking to you from a script that I've written. I just have some muscle memory, that's all. And to gain that muscle memory, you need to start using it. Okay? Cool. Finally, let's look at when not to use joints. I won't be taking much of your time here. Don't use joints for simple animations. Use animations instead or just a lerp. The reason why I made a configurable joint for the platform is for the jiggle physics. So think before you act. For controlled movement, use a kinematic rigid body. You see, joints are reactive, which makes them unpredictable sometimes. If you want control through code, use kinematic rigid bodies. For fake effects, like insane trampoline jump from Mario, simulate behavior with code, okay? It's far more easy and less taxing. Also, use joints only if you want it to be a mechanic. If it can be animated or scripted, that is often the better solution. Okay, that is all. Alright, we have talked about each joint type, how they behave and when to use them. Now let's look at how to actually control these joints through code. It's pretty simple. You can create an object of the specific type of joint that you want to create. You can get a joint like any other component using getComponent, or you can make it a serialized field to be able to assign it in the inspector and then tweak its properties in real time. An important thing to note is that the class joint inherits from component and not behavior, meaning they cannot be enabled or disabled. They can only be added or destroyed. Like any other object, you can access the properties using the dot operator and then access the properties and change them however you want. There are other properties like angle and stuff like that you can access. So if you are dealing with code, I just recommend scanning through all of the public variables available in the type of joint that you want to work with. Like I said, joint is a component, not a behavior, which means you can add component of a specific joint during runtime to create dynamic behavior. Like if you want to attach a weapon or grab something, you can add a joint like a fixed joint at runtime and then assign its connected body. You can also use joints for procedural animations and IK systems, but it's a little bit more complicated. And I've not worked with that before. I just know that these things could be possible. I have never tried it myself. If you want to disable or stop the joint behavior, the only way through code is to destroy the joint component itself. Also, too many joints can slow your script down. Try to keep it simple. Combine colliders, keep connected bodies light, and avoid complex joint chains unless absolutely necessary. Before we wrap up, let's talk about optimization, as I promised. While joints are powerful, they can also tank performance if you're not careful. And the obvious first thing to note is don't use more than what you need. Every joint adds physics calculations each frame. So if you have hundreds of joints, it gets expensive fast. The next step is to avoid deep joint chains. It's because they can be unpredictable and quite heavy. Consider alternatives like soft body simulations or fake the motion with animations and a few spring joints and stuff like that. Also, this is the biggest optimization tip, that is to sleep inactive bodies. Rigidbody has a sleep threshold that you can use and stop simulating physics. Because this is a component, you cannot disable it, but you can sleep the rigid body when they are inactive or when they're not needed. There is a little bit of optimization that Unity does behind the scenes, but you can set the rigidbody.sleep threshold wisely and when not in use. You can also call the rigidbody.sleep function to sleep a rigid body. You should also think about disabling the game object itself completely. That's a great optimization as well. Another tip is to reduce solver iterations. Unity tries to solve joint constraints every physics step. You can lower the solver iteration count and a solver velocity iteration count on the rigid body to reduce CPU usage. Okay, these are just variables that you can change to reduce the CPU usage of certain joint based calculations, but they will yield less accuracy. Okay, this is important for mobile and large scenes, but you should test because it affects the stability. Also, use interpolation carefully. Interpolation smooths rigid body motion, but it adds overhead. Only enable it on visible objects or if needed. Also, if you are adding joints at runtime, clean it up. Don't forget to remove them when no longer needed. This is because the simulation keeps running even for invisible or detached items. A few smart optimization can make the difference, right? Also, always learn how to profile your physics heavy scenes. If you are confused about profiling, you can check out this video on the top right. Okay, I've made it step by step and as beginner friendly as much as possible. And that's it. Joints in Unity might be scary, and it is scary, but once you get used to it, they open up a lot of possibilities. If you like this deep dive, consider subscribing and dropping a comment below. It would really keep me motivated to make more videos like these. Also, let me know what you're building with Unity joints if possible. You can share them on the Discord server. It would be fun to hang around and then, say hi. Alright, that's it for this video. If you like a video on 2D joints, please do let me know in the comments below, and I will work on it as soon as possible. Thank you so much for watching this video. It means a lot to me. Take care, and as always, I love you. Bye. Yeah.